Okay, in today's lesson, we're going to learn about rational functions. You're going to learn to find the domain of rational functions. Then you're going to learn to find vertical, horizontal, and slant asymptotes of rational functions. And then we're going to sketch the graph. And we're going to sketch that graph with vertical asymptotes using our vertical asymptotes, our horizontal asymptotes, our slant asymptotes, our y-intercepts, our zeros, additional points, and holes in the graph. So all this data is going to go together in order for us to sketch rational functions. So first, before that, let's review how to find the domain of rational functions. Well, the domain of a rational function is simply when the denominator is equal to 0. We covered this in Unit 1, so just to kind of review over that information, it's going to show up again. So for example 1, if I want to find the domain of f of x, I would set the denominator equal to 0, and I get x cannot be equal to 1. So from negative infinity to 1, union 1 to infinity would be my domain. Next, we're going to learn how to find the vertical asymptotes of rational functions. To find your vertical asymptotes, your first step is that you need to simplify the rational function, if it is possible. Not all rational functions can be simplified. Once you simplify the rational functions, your vertical asymptotes are wherever the denominator equals 0. So let's try a couple. We're going to find the vertical asymptotes of this first polynomial. First thing I notice is that I cannot simplify this polynomial. And so I will just take the denominator, which is x squared minus 1, and set that equal to 0 to find my vertical asymptotes. Notice it's the same process as finding our domain. The only difference is we do this after simplifying if the problem does simplify. And so our vertical asymptote, I can factor this difference of squares here and actually get two vertical asymptotes. We have one at x equals 1 and one at x equals 2. Vertical asymptotes are equations of lines, and they're always at x equals a number. So x equals negative 1 and x equals 1. You must write the x equals for each number, each one. The second one is an example of a rational function that will be simplified down. So I'm going to factor each of the polynomials, and I get the following. And notice that x plus 2 is in common in the top and the bottom, so I can cancel that out. Something cool happens when you cancel out a factor from the numerator and the denominator. And that's what we're going to talk about in a moment. So if you factor out the x plus 2 from the numerator and the denominator, it gives me a hole in the graph. How do you find the holes in a graph of a rational function? It's really easy. You find the hole in the graph by taking whatever factor cancels out, setting that equal to 0, and solving that factor. So here it would be x equals negative 2. That gives me the x value of the hole. Now to find the y value of the hole, I'm going to take negative 2 and plug it back into my simplified function. So it always plugs into the new function, the simplified function. So when I replace every x with negative 2 into this function, I get 3/5. So I have a hole in the graph at the point negative 2 and 3/5. Okay, what does that mean in terms of the graph? So how to graph a hole in the graph is at that value, at the negative 2, 3/5. Instead of drawing a closed-in dot like we normally do for points, we're going to draw an open circle to identify that point. So here's a quick example. That hole in the graph would be at this point here. All right, let's get back to the original problem. That was just a side note of how to find a hole in the graph since that's the first one we had a factor. Let's find our vertical asymptote to our original problem here. So you always go to the simplified equation, set the denominator equal to 0, and solve. And so our vertical asymptote is x equals 3. Now notice my domain of this function is still the original. Domain is all real numbers except negative 3 and the negative 2. Next, I'm going to find the horizontal asymptotes of a rational function. To do this, I'm going to let the polynomial in the numerator be called n of x and the polynomial in the bottom be called d of x. First step is to simplify your rational function. You're going to see me say that a lot. You're always going to do the first step is simplifying the rational function. Then I'm going to compare the degree of the numerator polynomial with the degree of the denominator polynomial. And so I'm going to let little n represent the degree of my numerator polynomial. And I'm going to say my degree of my denominator polynomial, I'm going to call d in my notations below. So when the numerator's degree is less than the denominator's degree, y equals 0 is your horizontal asymptote. It's along the x-axis. So notice the difference here. Horizontal asymptotes are y equals, vertical asymptotes are x equals. If the degree of the numerator equals the degree of the denominator, you find your horizontal asymptotes by doing the simple equation. You take the leading coefficient of the numerator's polynomial and divide it by the leading coefficient of the denominator's polynomial. When the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptotes in the problem. So back to these two original problems that we started with, we're going to find our horizontal asymptotes. We already found vertical, so let's find our horizontal asymptote. So the degree of the numerator is 2. The degree of the denominator is also 2. So n is equal to d in this problem. So that means I'm going to take my horizontal asymptote is going to be y equals the leading coefficient of my numerator, which is 2 in this case, divided by the leading coefficient of my denominator, which is 1. So y equals 2 would be my horizontal asymptote, which you can abbreviate HA, for this problem. Now remember, we have to simplify first. We have already simplified this polynomial, this rational function, so I'm just going to do it really quickly. So again, we're looking at the simplified polynomial of x minus 1 divided by x minus 3. So our degree of the numerator is 1, degree of the denominator is also 1. So the numerator's degree is equal to the denominator's degree. So horizontal asymptote is equal to 1 over 1, which is y equals 1. Again, you must write the horizontal asymptote as an equation, and the equation is y equals. Now, the third type of asymptote is called a slant asymptote. It's a diagonal line, a slanted line. This will only occur if the degree of the numerator is exactly 1 more than the degree of the denominator. So remember, when the degree of the numerator was greater than the degree of the denominator, you have no horizontal asymptote. But in the case that if the degree of the numerator is exactly 1 more than the degree of the denominator, so n is equal to d plus 1, then you will have a slant asymptote. And you find your slant asymptote by doing long division. So we're going to divide our bottom polynomial into our top polynomial, using either long or synthetic division. Doesn't matter, just don't divide them, and it will disregard the remainder, and whatever polynomial is left over will be our function. So I see if this is a new one, so I try to simplify it, but nothing cancels out, so it really cannot be simplified. So I'll go back to my original problem. And so I noticed that my degree of my numerator problem here is 2, so n equals 2, and degree of the denominator is 1. So 2 is greater than 1, no horizontal asymptote. But I also noticed that n is equal to d plus 1. So 2 is equal to 1 plus 1. So it's just 1 greater. So that tells me I'm having a slant asymptote. So I need to divide the denominator polynomial into the numerator polynomial. I'm going to do long division this time. I mean synthetic division. So I set up my synthetic division. And I disregard the remainder. I just throw it out. It doesn't mean anything in this problem. And I put my x's back in. So I started with an x squared, so now it's an x. So the line y equals x minus 2 is my slant asymptote for this problem. Okay, now we're going to look at graphing rational functions by hand. So step 1, simplify if possible. Simplify the rational function if possible. Remember, any factors that cancel out will represent holes in the graph. So if you cancel any factors out, you need to find the holes in the graph and plot them on your graph as open circles. Next, I'm going to find the asymptotes of my function. And so you must find your vertical asymptote. And then if it has a horizontal asymptote, find the horizontal asymptote. And if it has a slant asymptote, find the slant asymptotes. Once you find those asymptotes, the next is you're going to find and plot your y-intercepts, if they have any y-intercepts. And remember, how to find y-intercepts, that's when your x is equal to 0. So you're going to be by evaluating the function f of 0. So your simplified equation, just replace every x with 0 and get your answer. Then you're going to find the zeros of the rational function is going to be equal to whenever the numerator equals 0. Because the only time a fraction will equal 0 is if the top of the fraction is 0. So I'm just going to take the top of the fraction and set it equal to 0. These are our zeros of our function. Remember, is another name for x-intercepts. Okay, then we're going to plot at least one point between and beyond each x-intercept and vertical asymptote. So every time we have something going through the x-axis, we need a point in between and beyond each of those values. Once we have that, we're then going to use our knowledge of asymptotes and those points, and we're going to draw smooth curves connecting the points and approaching the asymptotes to complete our graph. So let me walk you through a few examples. So starting with g of x is equal to 3 divided by x minus 2. Step 1, see if it simplifies. Well, no, it doesn't simplify. So then I'm going to find my vertical asymptotes by setting my denominator equal to 0, and I get a vertical asymptote at x equals 2. Then I'm going to find horizontal asymptote. So I'm comparing the degree of the numerator, which is 0 in this case, and the degree of the denominator, which is 1. So since the degree of the numerator is less than the degree of the denominator, my answer for horizontal asymptote is y equals 0. Since I have a horizontal asymptote, I will not have a slant asymptote. So now I need to find my y-intercepts for the graph. To find your y-intercepts, you just replace every x with 0. So I'm going to find g of 0, which gives me negative 3 halves. So I have the point 0, negative 3 halves on my graph. That's my y-intercept. Now I'm going to find the zeros of the rational function. To do this, I take the numerator and set it equal to 0. So 3 equals 0. Wait, 3 equals 0? That doesn't make sense. 3 cannot equal 0. So in this case, this rational function has no zeros. The graph will never intersect the x-axis. Now I need to find additional points. So to figure out which additional points I need to use, I'm going to graph my all the data I have so far. So if you had holes in the graph, you graph the holes. If you have, you'll graph all your asymptotes and all your y-intercepts and zeros. So here all I have is a vertical asymptote at x equals 2. We graph all our asymptotes as dashed lines on our graph. And then I have a horizontal asymptote at y equals 0. Now, mine's a different color so you can see it, but you will use the same color pens. I want you to draw it really thick anytime it's on one of the asymptotes are on one of the axes. So I drew it really thick so you can see that. And the only other data I got was my y-intercept at 0 and -3/2. Okay. So additional points, I need to find a point beyond in between every x-intercept and vertical asymptote. So that y-intercept is already a point to the left of that vertical asymptote. So all I need to do is find a point to the right of the vertical asymptote. I'm going to choose 3. And so when I solve that out, I get 3 equals 3. And so I'm going to plot a point at 3, 3. Now, remember from our parent function of rational function, they kind of have two U shapes. So I'm going to draw my U shape, starting at an asymptote, going through the point I have plotted, and approaching the next asymptote. So this would be the graph of g of x. Okay, starting with this one, this function also does not simplify. So I want you to find your vertical asymptotes. Let's see how you did. Your vertical asymptote is when the denominator equals 0, so the answer is y equals 0. Find your horizontal asymptotes. Y equals 2 is your horizontal asymptote. Next, we need to find our y-intercepts. Ooh, -1 over 0, that is undefined, so this one has no y-intercepts. Now find your zeros. Remember, you find your zeros by taking your numerator and setting it equal to 0 and solving for x, and I get x equals 1/2. So I have the point 1/2 comma 0, so x-intercept of 1/2. Now I need to figure out additional points. So to figure out additional points, I'm going to go to my graph and I'm going to plot the data I have so far. So I have a vertical asymptote at x equals 0. So that's my y-axis. So again, draw it really thick so I can see it. Dashed lines for all asymptotes. And then I have a horizontal asymptote at y equals 2. No y-intercept, that makes sense because it's an asymptote. And a 0 at 1/2. Something to the left of that vertical asymptote at 0. So I just need to plug in some value less than 0 into my original function, or my simplified function, which is the original in this case. I'm going to choose -1. Plugging that in, I get 3. So I have the point -1 comma 3 on my graph. Now I need a point between my x-intercept and my vertical asymptote. So I chose 1/4 because we need it between and beyond every asymptote and x-intercept. Working out f of 1/4, you end up with -2. So I have the point 1/4 -2 on my graph, so we can plot that. And our last x-intercept, our last one is we need some value greater than our x-intercept there. So I'm going to choose 2. Plugging that in, I get the point 2 comma 3/2. So now I want to plot all those additional points onto my graph. And I'm going to use a smooth curve, approaching my asymptotes, going through the point that's given. And there is our rational function, f of x. Okay, let's try another one. So again, this one will not simplify, so I'm going to start by finding vertical asymptote. This is the first example where we have a quadratic in the denominator. It simplifies down to x equals 2 and x equals -1. So this equation has 2 vertical asymptotes, so our graph is going to look a little different. Find your horizontal asymptotes. Since the degree of the numerator is less than the degree of the denominator, I have a horizontal asymptote at y equals 0. Find your y-intercept. So I find my y-intercept by replacing every x with 0 and simplifying it down. 0 over -2 is 0. So my x-intercept is at the point 0, 0. Now find your zeros. You find your zeros by taking your numerator and setting it equal to 0. In this case, x equals 0. All right, so let's plot the information that we have so I can figure out what kind of additional points I need to find. Remember to sketch your asymptotes as dashed lines. So I have two vertical asymptotes, one at x equals 2, next one at x equals -1, and a horizontal asymptote at y equals 0. I'm going to do it really thick because it's on my x-axis. And then I have my x-intercept at 0, 0. Now notice I do have, that point is on my horizontal asymptote. Yes, graphs can cross the horizontal asymptote in between two vertical asymptotes. It only happens in between vertical asymptotes. So now I need to find a point beyond in between each of my x-intercepts. So at beyond my first vertical asymptote is -2. Between my vertical asymptote and x-intercept, I'm going to do -1/2. Between my x-intercept and the second vertical asymptote, I'm going to choose 1. And beyond my last vertical asymptote, I'm going to choose 3. And then I'm just going to plug it into the equation. My first additional point is -2, -1/2. Plot that on my graph. Now notice I can plug this into my original equation or into my factored equation. I chose my factor because it's easier for me to work with fractions with subtraction and addition than it is with squaring, but you could do either one. And so I got -1/2 and 2/5. So I'll plot that on my graph. Then replacing every x with 1. Notice this time I plugged it into original equation, so you can see that you can plug it in whichever way you want. You'll get the same answer. So now I have the point 1, -1/2 on my graph. And finally, replacing every x with 3. I get the point 3, 3/4. So I'm going to plot that on my graph. And so this one's going to have 3 parts to the graph. So I have a kind of curve shape starting at my asymptote, going through that first point of -2, -1/2, then approaching the asymptote. Then starting at my asymptote, going through those 3 points and approaching that asymptote. And make sure that that is not a straight line, it's curved and smooth. So always draw smooth lines as you're approaching asymptotes. Notice I can cross over a horizontal asymptote as long as it's between two vertical asymptotes. And then my last curve. Just kind of approach it, starts at an asymptote, goes through the point, and then approaches the next asymptote. Yeah. There you go. I like that one. All right, let's try one more. Oh, 2 more, sorry. All right, so for example D, I think this one will factor first. So I need to simplify f of x here. So I need to factor my numerator, which is a difference of squares. So it's going to be x minus 2 times x plus 2. And then factor my denominator. Gives me x plus 2 times x minus 3. So x plus 2 cancels out. I have a hole in the graph, so I have to add this step of finding the hole. Remember, you find the hole by setting what cancels out equal to 0 and solve for x. That gives you the x value of your hole. And then once you have that x value of the hole, you're going to find the f of -2 by substituting it into the simplified equation. So I have a hole in the graph at the point -2, 4/5. Now I have a simplified equation. I'm going to find my vertical asymptote. My vertical asymptote for this problem is x equals 3. Now let's see if we have horizontal asymptote. Degree of the top is 1, degree of the bottom is 1. They are equal, so it's equal to 1/1. So y is equal to 1 is my horizontal asymptote. Must be written as an equation. Okay, next step, find your y-intercepts if you have them. So to find your y-intercepts, you just evaluate f of 0, replace every x with 0, and then simplify down. Make sure you're using your simplified equation. And I get 2/3 as my answer. So 0, 2/3 is my y-intercept. To find your zeros, you take your numerator of your simplified equation, set it equals 0, and solve, and you get x equals 2 is a 0. Okay, next step is to find additional points. So before I can find these additional points, I need to graph the data I have so far to figure out what values I need beyond and between every vertical asymptote and x-intercept. So start by graphing our hole in our graph and our vertical asymptotes. So our hole in the graph is at -2 and 4/5. So I draw an open circle for the holes in the graph. I have a vertical asymptote at x equals 3, so a dashed line there. Vertical asymptote at y equals 1, so a dashed line there. Y-intercept at 0 and 2/3, so put a dot. A 0 at x at 2, so put a dot there. So the y-intercept is already a point to the left of my x-intercept, so I'm good for that piece. So I now just need a value in between my 0 and my x-intercept and my vertical asymptote. I'll choose 2.5. And so I get the point 2.5 comma -1, plotted that, and gave that side of the curve. So now I'm just missing 1 point beyond my vertical asymptote. I chose 4, and I got 2 as the answer. So I'm going to plot the point 4, 2 on my graph, and then draw a curve from my asymptote through that point, approaching the next asymptote. And you're done with that graph. Okay, for example E, we're going to start and see if we can simplify it. And no, it will not simplify down. So now we're going to find our vertical asymptotes. So vertical asymptotes when the denominator equals 0, so it's x equals 0. Find horizontal asymptotes. The degree of the numerator is 2, the degree of the denominator is 1, degree of the numerator is greater than the degree of the denominator, so therefore there is no horizontal asymptote in this graph. So now if there's no horizontal, I need to check and see if I have a slant asymptote. Since the degree of the numerator is exactly 1 degree more than the degree of my denominator, so since n is equal to d plus 1, I do have a slant asymptote. Find the slant asymptote. Now, because my denominator is x, which would be, if I did synthetic division, would give me a 0 on the outside, I can't do this with synthetic division. So I'm going to have to actually use long division to find my slant asymptote here. So setting this up for long division. So how many, if I multiply x by 3x, it gives me 3x squared. Strike that, gives me 0. Bring down my next term is 0x. Multiply x times 0 to get 0x, and that's it. Now my result is 1, which has a degree smaller than the outside, so I know I'm stopped. So we disregard the remainder and just write our equation. So y is equal to 3x. So y equals 3x is your slant asymptote for this problem. Our next step is to find our y-intercepts. Remember to find your y-intercepts by replacing every x with 0 in your simplified polynomial. Ooh, 1 over 0. That you cannot divide by 0, so that means there is no y-intercept for this problem. Now let's find the zeros. To find your zeros of the polynomial, you take your numerator polynomial and set it equals 0. To find the zeros of the rational function, take the numerator polynomial and set it equals 0. Ooh, I get x squared is equal to -1/3. So when I take a square root of a negative, I get i's. That's an imaginary number. Imaginary numbers cannot be graphed on the real number plane. So anytime you get a 0 that's an imaginary, there are no real zeros for this polynomial. The imaginary numbers never show up on our graph. So this tells us our graph will never intersect the x-axis. Okay, now we need to find some additional points. So I'm going to start by, again, graphing the data I have so far in this problem. So I have a vertical asymptote at x equals 0. So draw it really thick on your y-axis. There's no horizontal asymptote, but there's a slant asymptote at y equals 3x. So use the y equals mx plus b form. I have a y-intercept of 0, rise of a slope of 3. So that means I run up 3, rise 3, run across 1. Do a few dots there so I can draw this dashed line. Now realize that these dots here are not part of my graph function itself. They're just helping me draw my asymptote, the dashed line. All right, so now I got to figure out our values. So I don't have any x-intercepts, so I just have a vertical asymptote. So I need to find a value to the left of my vertical asymptote and a value to the right of my vertical asymptote. So you can choose any values you want. Closer to the vertical asymptotes fit better on the graph. So I'm going to choose to plug in, say, f of -1. So plugging in -1 into here, into my function, and simplifying that down, I get -4. So I'm going to plot the point -1, -4 on my graph. And then I choose a number on the other side, so I'm going to choose 1. Plugging in 1 into the polynomial, a rational function, I get 4, so I have the point 1, 4. So again, I'm going to start at my asymptote, go through the point, and then go to the next asymptote. Start at my asymptote, through the point, approach the next asymptote. So those are my only choices. So I have these two u's going away from each other, would be the graph of this function.